Hello everyone. Today we are going to be talking about the equations of motion. So the objectives for today are to be able to solve kinematic equations for objects traveling in a straight line with a constant acceleration. One of the equations you already know, and that's average velocity is equal to distance divided by time. And if you recall, this equation comes from the graph of distance divided by time, and that's the slope of that line is just the average velocity. However, it is only average speed or velocity, and it only works if it's stated as average or if it's at a constant speed. Sometimes, though, we need to incorporate acceleration. Acceleration is a change in velocity. To change velocity, we could speed up or slow down. You may know this as decelerating or having a negative acceleration. In physics, we only say negative acceleration. Or you could change the direction of the velocity. So the most basic equation for acceleration is the change in velocity divided by time. This comes from the velocity versus time graph, the slope of that line. But the units are meters per second squared. Meters per second squared is not something that we usually deal with, but if we think about it, that just means that it is meters per second. That's how it works. All right, so we have 5 equations we're going to be working with. We already talked about the average velocity is equal to the distance divided by time, and the acceleration is equal to the change in velocity divided by time. We also have the final velocity is equal to the initial velocity plus acceleration times time. This is the same as this one, it's just rearranged. And then we also have distance is equal to the initial velocity times time plus 1/2 times acceleration times time squared. And then we have the final velocity squared is equal to the initial velocity squared plus 2 times acceleration times distance. If you notice on the right hand side, all of the symbols are listed here with their definitions, and that's true in the reference table too. These equations are on page 6 of your reference table at the very back. Okay, so here's our first problem. It says a car goes from 0 meters per second to 100 meters per second in 5 seconds. What is the acceleration? Well, we need a strategy first. So in physics, we often have a kind of standard way of approaching a word problem. First, we need to draw a picture if we can, then list the knowns, what are you given and what do you know, and the unknowns, what are you looking for. Identify the equation you want to use, and then manipulate the equation or solve for your variable. Plug in your known values, and then solve and report your answer with units. So here's our equation again. It says a car goes from 0 meters per second to 100 meters per second in 5 seconds. What is the acceleration? Well, let's write down, first let's draw a picture. So here's the car, and you will soon find that my drawing skills are almost non-existent. I think you can recognize this as a car though, so that's a plus. And then the car goes to the right, and we're calling this the positive direction. So then we can write our knowns, and we know that the initial velocity is 0 meters per second. The final velocity is equal to 100 meters per second. And then the time is equal to 5 seconds. And we're looking for acceleration. So acceleration is, I don't know. If we bring up our equations, we can look for something that has initial velocity, final velocity, time, and acceleration. We see it as this one here with final velocity equals initial velocity plus AT, but this equation here, A equals change in velocity over time, is the same thing, but it's already solved for A for us, so we don't even have to worry about anything. So if we plug things in, it's A equals the final velocity is 100 meters per second minus 0 meters per second divided by 5 seconds. Well, 100 divided by 5 is 20, and the units for acceleration are meters per second squared, so we could go about it like this. However, we can do even better and check with unit analysis. So meters per second, so if we multiply it, it's going to be 1 over the value, so 1 over second. So then that's meters per second squared, which is exactly what we want. So this makes sense, which makes this makes us confident in our answers, and we can go forward. So then the next equation is final velocity equals initial velocity plus AT, and we need to assign a direction for positive and negative. And here is the problem. It says, what is the exit velocity of a bullet after it travels down a rifle barrel with an acceleration of 2 times 10 to the 5th meters per second squared in a time of 0.03 seconds? Okay, so we want a bullet. Oh, it's a rifle barrel. I didn't realize that. That makes it a little easier for me to draw. I know a little bit better what that looks like. Not quite long enough for rifle, but it's all right. The bullet comes out like that, and it's going to the right. And now we can write our knowns and unknowns. So the initial velocity is going to be 0 because the bullet's not moving to begin with. And then we have an acceleration of 2.0 times 10 to the 5th meters per second squared, and a time of 0.003 seconds. And we are looking for the exit velocity, and that's going to be the final velocity. So it's VF equals, I don't know. So the equation we're working with is VF equals VI plus AT. This VI is going to go to 0. So then we have the final velocity is equal to acceleration times time. And then we just plug in the numbers. Acceleration is 2.0 times 10 to the 5th meters per second squared. And I'm just going to get rid of that stray mark there. And (2.0) times 10 to the 5th meters per second squared. So then that's times time. The time is 0.003 seconds. And then that is equal to 600 meters per second when we plug that into the calculator. So we want to check and see if this is reasonable. So we have meters per second squared, and then we multiply it by seconds. So this seconds gets rid of one of these seconds, and we end up with meters per second, which is exactly what we want. So we can be confident that this is at least somewhat okay, as long as we didn't mess up the calculator. So then the next equation is the distance is equal to the initial velocity times time plus 1/2 times the acceleration times time squared. So this problem says a model rocket provides an acceleration of 35 meters per second squared for 6 seconds. How high does the rocket reach when the engine cuts off? So our rocket, and I can draw a sci-fi-ish rocket, sort of, maybe it'll look more like a squid. That's okay. Anyway, I was trying to go for Robert Heinlein here, but I think I failed. But that's all right. It's a rocket. Up is the positive direction. And we can write our knowns. It says an acceleration is 35 meters per second squared for this rocket. And it's going to go for t equals 6 seconds. And then it asks for how high the rocket reaches when the engine cuts off. So this is going to be a distance that we're looking for. And the initial velocity is still 0 meters per second. It starts off at 0 at the bottom. So the equation we want that makes sense is distance is equal to initial velocity times time plus 1/2 times acceleration times time squared. This initial velocity goes to 0 because the initial velocity time is 0, so it gets rid of it for time too. Then distance is equal to 1/2 times 35 meters per second squared times 6 seconds, and that's squared. And then this is equal to 630 meters when we put that into the calculator. But again, we want to check our units. So it's meters per second squared times the second is squared because of the squared on the outside. These two cancel, and we end up with meters, which is exactly what we want. So that makes sense. And we can be confident in our answer. Now the last equation is VF squared equals VI squared plus 2AD. Here we have a potato cannon. And I don't know if you've seen a potato cannon, but they're pretty long. we're just going to go with it and say that that's the background, that's the horizon there. And then the potato comes out and it's going to the right, and that's the positive direction. So then our knowns, it says a potato cannon accelerates down a 1.2 meter tube, so that's distance is equal to 1.2 meters. And then the acceleration is 1041 meters per second squared. The initial velocity is still 0 meters per second. And then the final velocity, that's what we're looking for. So the equation we're using is VF squared equals VI squared plus 2AD. Oops. Okay, this goes to 0. So then it's VF is equal to the square root of 2 times A times D. So then it's 2 times 1041 meters per second squared times distance, which is 1.2 meters. Okay, so then when we plug this in, we end up getting 49.98 meters per second. And again, we want to check our units. So it's meters per second squared times a meter. So we get meters squared per second squared, but then it's square rooted. So we get meters per second, which is what we want. So this makes sense for this one. And then the last part says how much time does it take for it to go 100 meters? So then we have some new knowns and unknowns to add in. And we're going to use D equals VIT plus 1/2 AT squared. This is still 0. The distance is 100. So now we have to actually solve for the time. So it's going to be 1/2 AT squared. So the reciprocal of 1/2 is 2, and that'll get rid of the 2 on this side. We can multiply by 2 on the other side. So then it's 2D. Hold on. Sorry, it is 2D is equal to AT squared divided by A. So then T is equal to the square root of 2 times the distance divided by the acceleration. And it is 2 times 100 meters divided by 1041 meters per second squared. And that, when you plug it into the calculator, gives you 0.44 seconds. And again, we want to check our units. So on the bottom, we have meters divided by meters per second squared, but we flip it so it becomes 7 seconds squared divided by meters, and we flipped it just because it's on the bottom of this fraction. And then this gets rid of the meters, so then it's seconds squared, but we're taking the square root, so that's seconds, and that is the unit we want. So this